A relevant result on the other side of the city is still the wrong result. Typesense Geosearch filters by radius and ranks nearby matches by distance from Python. You'll see how to connect the pieces into a workflow that stores places and ranks nearby matches by distance with text tie breaks. I'm Professor Pi, teaching search and IR with simple Python. Many apps need a sharper sense of what near me actually means. A plain keyword match can happily send your user across town. Nearby place search fixes that by combining geographic distance with text relevance. So nearby, relevant places rise to the top. Typesense is a compact, fast search server that already understands geographic points and text relevance. That saves you from building spatial indexing from scratch and gives predictable local results with low latency. Imagine a user typing coffee near me. We want candidates inside a radius, then prefer the closest ones, but still respect the query words. The flow is filter by distance, sort by distance, and use text relevance to break ties. That gives practical, predictable rankings you can tune. We will build a tiny demo end-to-end. Connect Python to Typesense, define a places collection with a geopoint field, write a few sample places, run a radius-limited search, and then combine distance buckets with text relevance. It maps directly to how a mobile or web app would show local results. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. So first, let us prove we can talk to a running Typesense node and check the connection. This snippet connects Python to a local Typesense node and confirms the client can reach it. The snippet puts the host, port, and protocol into the node dictionary, so the connection details are explicit. Then, it builds the official Typesense Python client with typesense.client, so the client object is wired to that node and to your API key. A lightweight call like client.collections.retrieve is used as the smoke test because it only reads metadata and does not mutate state. If the call returns, you see that Typesense responded, and that lets you trust later schema creation and document writes. Nearby place search only works if the search service, API key, and client wiring are all pointed at the same running node. Now that the client responds, we need a proper schema that stores location as geography, not text. This example creates the Typesense Places collection with a real geopoint field. The schema is deliberate. Location must be indexed as a geopoint, so Typesense can apply radius filters and compute distances. The schema also marks name and kind as searchable text fields, and keeps popularity as a numeric field we can use later for ranking experiments. The snippet includes a small delete block, so you can rerun the demo without hitting a duplicate collection error. When the create call completes, Typesense confirms the location field was accepted as geopoint, which is the required primitive for radius filters and geo-sorting. With the collection ready, we need real documents to return in searches. This code writes a tiny set of places into Typesense using documents.upsert. Each document includes a location value as a latitude-longitude pair, and that ordering matters because swapping lat and lon will silently wreck distance calculations. The toy dataset intentionally mixes a very close cafe, a slightly farther coffee place, and a nearby but textually different bookshop so we can test both geo and text behavior. The code collects returned IDs into saved and prints them, which proves the right path reached Typesense, and the documents are indexed. The printed IDs are what later searches will match against. Now test a real query. Coffee within 1 kilometer of a point. This snippet asks Typesense for coffee-related places within 1 kilometer of near. The query uses filter by to drop faraway candidates before any ranking happens, so you do not waste scoring on irrelevant distant items. Then, sort by orders, the remaining hits by distance from the same point. And the returned geo-distance meters gives a real metric you can show to users. The radius is an important knob. Increasing it boosts recall by admitting more candidates, but it can show less local results. Decreasing it makes results stricter and might hide useful nearby matches. The visible output shows the closest matching place and its distance, which is the core behavior for a local search. Finally, we refine ranking so text relevance matters among truly nearby places. This example turns naive distance sorting into a more balanced Typesense ranking baseline. Instead of letting every meter decide the order, the snippet buckets distances using precision. 1 kilometer, so very small distance differences do not automatically outrank better text matches. The sort then uses a combined key, like geo-precision first and underscore text match desc, as a tiebreaker. So Typesense pulls in text relevance when distances are comparable. A larger precision value gives text more influence. A smaller precision forces stricter nearest first ordering. The printed top two names show how combined geo and text ranking changes the order, which is exactly what you need for practical near-me retrieval. In a real project, you would swap the tiny demo data for a city POI extract, such as an OpenStreetMap place stub, and run these same calls at larger scale. The same schema and search pattern map directly to a service that answers hundreds of queries per second. What we built, in short, it is a radius-filtered, distance-ranked search pipeline with text tiebreaks. Use this when you need local relevance for place queries that must respect physical distance. One caveat is that the precision parameter trades strictness for text influence, so tune it for your user expectations. To extend this example, run the demo on an OpenStreetMap POI extract and tune the precision parameter from precision 1 kilometer towards smaller values while measuring user relevance on a held-out query set. That single experiment yields the biggest practical improvement. If short practical IR helps, subscribe and watch the IR videos.